Chemistry 4.1. This unit is kind of weird in that there's no route to teach each one individually, but once you know how to do it, you know how to do everything. I'm here using my hands like you can see me pointing. Um, but still, the same way you head up your book, get the objectives down or get the syllabus points down, and then we'll get to it. So, stoichiometry, it's about writing chemical equations and writing the formula and speaking the chemistry language, so to speak. So let me hit pause and sort. Alright, so this is your vocabulary, and it's your periodic table, and you'll notice it's a little small so you can't see, but each square has two numbers, a set of letters, and a word. And the word is the chemical name, the letters are the chemical symbol, and the numbers are, the atomic mass and the molecular mass. So let's get started. Whenever you get a molecule, alright? Let's say, for example, I have a molecule of CO2. So I'm going to draw it for you. A molecule of CO2. Now, there's a way that we can write this. You can say 1 carbon and 2 oxygen. But that'll take you forever, especially if you have something huge like glucose. So what we do in chemistry is we use symbols to say what we want to say, and then we put numbers in places that we want them to go. So 1 carbon, I would use the chemical symbol for carbon. And then there are 2 oxygens, I would use the chemical symbol for oxygen. Now what I then do is add in some numbers to tell me. Now I'm going to do an imaginary 1 right there, 1 carbon, and an imaginary 2 right there. Okay? Now just like in math, whenever you have the number 1, there's no need to put it there. In math if you have 1x, you can just call that x. But if you have 2x, it has to be called 2x. Alright? So just like in math, for chemistry, we do the same thing. Whenever you have a 1, there's no need to show it. So what we have is CO2, carbon dioxide. Now if I turned around and did this, every time. If you turn around and did this, another carbon and another 2 oxygens. Now I have to somehow tell you, because you can't see molecules, that there are 2 of these guys, number 1 and number 2. And what we do in chemistry is we use big numbers in front. 2 carbons, dioxides. And what this 2 does, it doubles whatever it's in front of. 2 carbon dioxides. Okay? So now I have CaSO4. Actually, there's something really wrong with that. Hold on. Alright, so if I wanted to write the chemical formula for this, what we do is we start to list out what we see. We see S, we see Ca, and we see O, and then we write down how many numbers we see. 1S, 1A, 4 O's, and of course you can erase your 1s. And that's actually not how you say it. There are 4 rules that tell you how to order what you have, and I'll put the rules up now. Okay, so those are your rules for naming chemical compounds, so let's test them. We have this set up the way we see it. Metal comes first, so you'll go back to your periodic table to see which ones are metals, and we see that calcium is a metal, so we have to put calcium first, Ca. If there is no metal, then then hydrogen has to come first. So let's say there was no metal in this one, hydrogen comes first. If there's no hydrogen, then the lower group number comes first, and you would have to look on the periodic. How do I keep doing that? Look on the periodic table at your group numbers, whichever element is in the lowest number, that one comes first. And then if they're both in the same group, whoever's the lowest on the periodic table, their name comes first. So it seems silly, but you have to name them the right way. So now we have S and O4, so we need to know who comes next. The metal's already done, so we find S and O and we realize they're both here. So if they're both in the same group, let's check our rule. Whoever's lowest on the table comes first. So the S and then the O4. So CaSO4. Alright, so that's how you figure out names and how you put together your formula. Okay, so we now have to, that was how you figure out your formula based on graphical representation. So if I show you a picture of the molecule, can you give me a symbol and of course the word calcium sulfate? Why is the oxygen 8 and not sulfide? Because when you add oxygen you have to say 8. I don't know. Oops, wrong one. So now we have to move on to valency. Let's say I gave you the word magnesium chloride. You need to figure out for magnesium chloride how many magnesiums and how many chlorines. And in order to do that, you have to use the valency. So what valencies are, they correspond with the group numbers. And basically what it tells you is how many electrons need to be added or subtracted in order to, I guess it does tell you that. It tells you the charge of the ions. So if you look in group 1, anyone in group 1 has 1 electron in the outer shell. So they have to get rid of that 1 electron to have a complete outer shell, to reach that point of noble gas status. So when they get rid of that electron, they become +1. And in group 2, they have 2 electrons in their outer shell. They need to get rid of 2. And once they do get rid of 2, they will have +2. Now in all honesty, the pluses and the minuses do just make it difficult for no reason. It's a little hint. 3, because when you get to the 4th, you have 2 options, gain 4 or lose 4. So a valency of 4. And then when you get to group 5, they're not going to lose 5 electrons. They're going to gain 3. Group 6, they're going to gain 2. Group 7, they're going to gain 1. Group 8, they're going to gain 0. So now what we have are these numbers that are almost the same as the valency and the group numbers. They're almost identical. But you'll notice is that as they go up, once they get to 4, they start to go down. So if you just know your valency table, what I get my S1s to do is on our periodic table, we actually write valency right here and then put it in. 1, 2, 3, 4, 3, 2, 1, 0. It just makes life that little bit easier for you to, because I let them use their periodic table in tests and during class. You get 1 copy on a piece of card and then you just keep using it. You can write whatever notes you want. I get them to label their groups, you know, the alkali earth metals, alkali metals, halogens, etc. It just helps you to get used to your periodic table. But I digress. So yes, now you have these valency numbers. You have a table and you have some valency numbers. So now to figure out how many magnesiums and how many chlorines go together, you use the valencies. So magnesium and chlorine. They call this the hook and ladder. You can call it whatever you want, but that's what I call it. So magnesium, you have to figure out what group it's in. It's in group 2, so it has a valency of 2. And chlorine is in group 7, so it has a valency of 1. And then you write out the words, or you put the symbols next to each other, Mg and Cl. You know Mg goes first because it's a metal, and then you do the hook and ladder. You take the number from the first one, and you put it right there. And you take the number from the second one, and you put it right there. So that becomes a 1, and that becomes a 2. So your formula is MgCl2 for magnesium chloride. Remember, you don't have to say the 1, it's just like math. So now let's try aluminium oxide, Al and O. Whoops. And we check the groups. Aluminium is in group 3. Oxygen is in group 6. So we have a valency of 3 and 2. 3 and 2. And then you just write the symbols next to each other, but give yourself some space. And you do the old Al2, O3. Boom! That's how you deduce formula from words. Done. Now there are some instances where you may need to cancel down. Personally, I'd rather you just not cancel at all for those of you that are rushing to do this exam quickly. Anyone else, if you want to do some more work, you'll find out there are some rules and some regulations about what get cancelled and what doesn't. What do I mean by cancel? If you had something that came to, let's see. If you had something that had a 4 and then a 2, what you would normally do is cancel that down so that it's a 2 and a 1. But it doesn't always have to. Or you can even cancel the double 2's. You know what? Let's just do an example. So, calcium oxide, Ca and O. When you check your valencies, Ca is in group 2. O is in group 6, so the valencies are 2 and 2. Alrighty? So Ca and O, you get the valency numbers of 2 and 2. And then you write them out again. Oh, come on. CaO, and you do your swaps. What normally happens is the 2's actually go down to, I guess you could say, lowest terms, and you can say Ca1O1, which means CaO. That doesn't always happen, but it does always happen. There are a few specific people that do not cancel down, like H2O2. That's hydrogen peroxide. That doesn't cancel down, but Ca2O2 does cancel down. So that's why I don't like to get into it, because it's just the people that get to break the rules. Okay, so we just worked out the formula based on valency numbers. Now we're going to work it out based on ionic charges. So the ionic charges are just like the valency numbers, but they were what I were doing before, the pluses and the minuses. Okay, based on your, and of course 4 is going to be plus or minus, it doesn't really matter. It's that ambiguous one. So your valency number has something to do with the charge that you create. When you are an ion in group 1, you have a charge of +1, group 2 you have a charge of +2, etc, etc, etc. So we can also create formula based on the charges, and simply the fact that the charges have to match and create 0, but you do that the exact same way by doing the swap, and I'll show you in a sec. So let's do beryllium oxide. I hope I spelled beryllium right. Beryllium is Be, oxide is O. So now if we were to look at our charges, you would see that beryllium has a charge of 2 plus, and oxygen has a charge of 2 minus. So we do it again, BeO, and we do our swap, and you'll see it's Be2O2, cancel down, BeO. Now, it gets a bit more difficult because when it comes to the ionic, we have to introduce charged compounds, and I'm going to put the list. So this is your list of compound ions. What you need to recognize is that these guys come as a package, and the package has the charge. So the OH comes as a package and its charge is -1. The NO3 comes as a package and its charge is also -1. The SO4 comes as a package, its charge is -2, and you're starting to figure it out, eh? So they come as a package. You do not interfere with the N's and the H's, you just interfere with the charge. I mean, you could try to, you'll just realize that it's already done for you. So the same thing happens. And when we use chemistry and symbols to show our package, to show the package, we use brackets. So let's do it again on this side. Let's make ammonium oxide. Alright? Oops, wrong way. So boom. Ammonium oxide we set about the same way. NH4 and O. Now let's check our table. What was the charge for ammonium? +1. What's our charge for oxygen? 2 minus, -2. So then we do the exact same thing. NH4, O. Now to show our package, put it in brackets. And then we do our swap. And we have ammonium oxide. For those of you that were able to look around the outsides and look in, you'll realize that all we're doing is making the amount of positives match the amount of negatives. So ammonium has a +1. By having 2 NH4s, you now have +2. +2 and -2 make 0. So that's what happens. And what this bracket means is that you've got NH4, 1, 2, 3, 4, NH4, 1, 2, 3, 4, and then you've got, you know, your oxygen in the middle, oxygen. So NH4, 2, O1 or O. Alright? Once you're able to, the people that do best in chemistry, and it's a horrible story to tell, when I was in university, the people that did the best at the hard chemistry were the guys that were able to think in 3D. The people that can think around corners and think, instead of just looking at a piece of paper, they think of everything like a Rubik's Cube. It makes life a lot easier. Once you can see the molecules in your head and think in 3D, this thing can rotate, it has multiple pieces, chemistry gets a lot easier. So there are examples online of doing the compound ions and all that jazz. If you just remember that the box gets brackets. Box gets brackets. And if you want to, you can even put this stuff in boxes. I don't care. Box gets, no, you shouldn't. Actually, ignore that. I did not just say that. Box gets brackets. As long as you remember that the box gets brackets, you're fine. The number afterwards means how many of those guys. The big number in front means how many of everybody. I hope that makes sense. So if I have 2CO2, the little number, the 2, tells me how many oxygens I have. The big number, the big 2, tells me how many of everything I have. Alright? Bang! I wonder how much of the thing I think. Okay, last point. Molecular versus empirical. So your molecular compound, molecular, and your empirical. I can't spell empirical to save my life. I know there's a bunch of I's. Empirical. So your molecular formula and your empirical formula. Okay. Alright, so there is a definition in the syllabus, I'm guessing. Well, there should be. There probably is, I don't know. So the easy way to remember, molecular shows the number of everything there. The empirical shows you the ratio. And here's the example. Let's say I had, now I'm going to draw this a different way. Instead of doing the circles with the letters in it, we can just use the letters and the sticks to show that there's bonds. We have that. So if we had a molecular formula, we'd do what we always do. change the color. Count up what's there. 1, 2, 3, 4, 5, 6 H's and 2 the whatever, and you say H6 C2, and then you'll use your rules, and you'll see once you use your rules you'll write it out as C2H6. I feel like that's backwards to what the rule says, but I don't care. Okay, so that's your molecular formula. It's just a number that tells you everything that's there. But if you were to do some math, you'll realize that these cancel, and you can get C1H3, and that's your empirical. Okay, and basically what it says is, you can, let's say I had 50 of these guys, the empirical doesn't care. It just tells you that basically all of them follow this rule. While the molecular formula, if I had 50, it'd be, you know, C100 H300, right? So that's the molecular versus the empirical, or at least how I like to explain it. I'm probably wrong. Alright, I feel like this video is really long. Let's see how much of this we've done. Use symbols of the elements to write the formula, done. Determine the formula of an ionic compound, done. Deduce the formula from the relative numbers present, done. Construct equations with state symbols, no, we didn't do that. Deduce formula, simple compounds from a model, done. Deduce balancing, nope. Construct word equation, nope. Relative atomic, nope. No. So we've done the first half. Man, that took a long time. Alright, so I'll do the second half later.